Hey everyone, welcome back to my YouTube channel where I will be doing some calculus. Today we're proving the inverse trig derivatives which come up from time to time in differentiation. And so what is an inverse trig derivative? If you have something like y is equal to sine x as your normal operation, then your inverse would be sine inverse x, or as I write it, arc sine x, or even a sine x. It depends on the person. Different people use different notations. So in this video, we'll basically be finding the derivatives for all of them. And for that, we'll need to know our actual ratios of like sine, cosine, and tangent, and their reciprocals. So say we're taking this angle as our reference. This side is the opposite, this side is our adjacent, and this one's our hypotenuse. Sine theta is equal to O opposite over hypotenuse. Cosine theta is equal to adjacent over hypotenuse. Tangent theta is equal to opposite over adjacent. And then to get cosecant, we just flipped signs. So hypotenuse over opposite. Secant is just cosine flipped. And cotangent is just tangent flipped. So I'm just hoping that makes it a little bit easier. So now let's get into the actual derivatives. Say we have a function y is equal to arc secant x. That means x is equal to secant y. Now we need to differentiate this with respect to x on both sides. So the derivative of x with respect to x is equal to 1. And the derivative of secant y with respect to x, I'll start with sine, my bad. Secant is the hardest one and also the least frequent. So we'll start off with sine. So we have y is equal to arc sine x. So that means x is equal to sine y. And now if we were to differentiate both sides, when we differentiate x with respect to x, we get 1. And when we do the same with respect to y, so when we differentiate sine y with respect to x, we get cosine y multiplied by dy over dx. So now, if we were to solve for dy over dx, we get 1 over cosine y, which is secant y. So now we have a triangle and we have an angle y, but we want our function in terms of x. So we know that x is equal to sine y. So we'll take y as this angle over here. And sine is opposite over hypotenuse. So x is the opposite side and 1 is the hypotenuse. And now this would be 1 minus x squared all square rooted, because if we were to square this, it would be 1 minus x squared plus x squared is equal to 1, which fits the Pythagorean theorem. So now secant of y is just the adjacent, it is hypotenuse over adjacent because it's the reciprocal of cosine. So that means the derivative of sine inverse x is hypotenuse 1 over the square root of 1 minus x squared. So in short, the derivative of arc sine x is equal to this. And so I'm going to quickly do it for the other 5 derivatives. Please feel free to fast forward any of these because it might be a pretty long video because I'm doing all 6. So now we have arc cosine x, and it's basically the same logic for every single one. So that means x is equal to cosine y. If we differentiate both sides, we get 1. And if we differentiate cosine y with respect to x, it's negative sine y. But with chain rule or implicit differentiation, we get dy over dx as well. So that means dy over dx is equal to negative 1 over sine y. Now it's time to draw a triangle. Take this as our angle y, and cosine of y is equal to x over 1. So that means this is x, this is 1. This side is the square root of 1 minus x squared. And so now sine is opposite of our hypotenuse. So it's the square root of 1 minus x squared over 1. But we take the reciprocal of that. So it is negative 1 over the square root of 1 minus x squared. And I will rewrite this to cosecant actually. And since cosecant is hypotenuse over opposite, we get 1 over the square root of 1 minus x squared, but this negative carries over. So we have the negative of 1 over root 1 minus x squared as our derivative for cosine inverse. And notice how these are actually just the derivative for sine inverse and cosine inverse are just the negative of each other. If you were to multiply 1 by negative 1, you get the other one. So now let's move on to tangent. And this, I think this one is actually the easiest one. And it's the one that looks the nicest as well. So you have arctangent x. So that means x is equal to tangent y. Differentiate both sides, you get 1 is equal to secant squared y multiplied by dy over dx for reasons that I've already explained. So that means dy over dx is equal to 1 over secant squared y, which is just equal to cosine squared y. So now if we were to draw a triangle, this is the angle y, and then opposite over adjacent is x, so x and 1. And then that means this side has to be the square root of x squared plus 1. So that means cosine is adjacent over hypotenuse. So that means it is 1 over the square root of x squared plus 1. But then cosine is squared in our equation. So we square this. And so our final derivative for arctangent is equal to 1 over x squared plus 1. And this looks really neat, especially compared to arcsine and cosine. And as you'll see, compared to arcsecant and arccosecant. So arccot x, or like cotangent inverse, has the same logic. So in this case, you have negative cosecant squared as your derivative, and you now divide by negative cosecant squared y, meaning that this simplifies to negative sine squared y. And if we were to draw a triangle, cotangent is adjacent over opposite. So that means this side is now x and this side is 1. But our hypotenuse is actually the same. So that means we have sine, which is opposite over hypotenuse. And it looks almost the exact same. Once we square the sine, we get negative 1 over x squared plus 1. And that negative only comes because it carries over from the previous step. And I'll just show you the logic behind this. Because sine y is equal to 1 over root x squared plus 1, then we square it. The square root kind of cancels out. So the derivative of arc cotangent, when I say arc cotangent and cotangent inverse, that they mean the same thing. So now there are two more, and these two are objectively the ones that are most painful to work with, but they're also the ones that you'll see least, most likely. So good for whoever actually doesn't have to prove these. So we have y is equal to arc secant x. That means x is equal to secant y. Differentiate both sides and you get secant y multiplied by tangent y multiplied by dy over dx. So that means dy over dx is equal to 1 over secant y and tangent y. So now we have to draw a triangle again. And secant is hypotenuse over adjacent. So that means this is x and that is 1. So we have the square root of x squared plus 1, minus 1 as our opposite. And for some reason it looks like my screen isn't actually like acting up right now. Okay, it looks like it's back now. Okay, so we have x squared minus 1 because of how the Pythagorean theorem works. So that means the tangent of our angle, which is y, is this root x squared minus 1 over 1. And secant y, as was defined up here, is equal to x. So we have the derivative of arc secant x is equal to 1 over x multiplied by the square root of x squared minus 1. But since arc secant is only defined on a certain interval and it's always positive, we have this absolute value over here. So that means the last one is cosecant, and you can imagine the pattern that's used by cosecant. It'll probably be the negative of this derivative up here. But let's verify it. Y is equal to arc cosecant x. So that means x is equal to cosecant y. We differentiate both sides. And when I differentiate both sides, don't follow my example by not writing like the derivative operation each time, because I think that's very necessary to write in each step. I'm just getting a little bit lazy right now, and I'll probably do this in this step actually, just to like reinforce it. So we have the derivative of x, and then we have the derivative of cosecant y. So now that means we have 1 is equal to negative cosecant y, cotangent y, multiplied by dy over dx. And then we solve for dy over dx and we get this. So now cosecant y is actually just equal to x because that's in our question earlier on. Now if we were to draw our triangle, we get y as our angle, x as our hypotenuse, and 1 as our opposite side. And now that means we get x, the square root of x squared minus 1 as our adjacent. So that means cotangent of y is just adjacent over opposite. So that means we have the square root of x squared minus 1 over here. So that means we have 1 over x multiplied by x squared minus 1, all in a square root. And then like with arcsecant, we have the absolute value around this. And the reason for that is actually not what I mentioned before. It's more because if you notice the arcsecant graph, it well, I don't remember at the top of my head what it looks like right now, but in general, the arcsecant graph is meant to always be increasing, which is why that it has an absolute value around it. At least the way the domain was restricted, that's how it should be. But the the arccosecant graph is not like that because it's always decreasing. So now I guess this is it, and like I'll I'll try and quickly draw the arcsecant and arccosecant graph. So the secant graph looks a little bit like this. And it's defined from 0 to pi. Well, from when x is equal to 0 to pi. So now if we were to put this, make this graph like vertical, so now if we were to make this inverse, wait, never mind. In this case, the y is always increasing. So that means, sorry, in this case, the x is like increasing and the y is also increasing. From here to here, the y is always increasing. And the same case here. So that means the derivative for that has to be positive. And I'm not finding the right words at this stage, but I think that's the basic gist. And it's the opposite case for cosecant, which is why in both of these have absolute values around them. And arcsecant's derivative is positive at for its entire domain, and arccosecant's derivative is negative for its entire domain. Thank you so much for actually paying attention to this video, and keep practicing math. And if you have any questions or even just feedback about my explanations, please drop them in the comments. And by the way, unless you actually need to use these proofs for some quiz question, you can feel free to skip through a little bit to actually find out what they are. And just remember the actual derivative. Thank you for watching.